Hi, folks. Welcome back. Um, in this lesson, we're going to talk about galvanic and electrolytic cells, so batteries, essentially. Um, so galvanic or electrolytic, voltaic cell, however you want to call it. These are all um, sets of oxidation and reduction reactions that produce a voltage and allow electrons to flow through a circuit. We know that this is something that's going to produce or release energy spontaneously. Hopefully, to use a battery, you don't have to put energy into the battery during its operation, or else it wouldn't really be a battery, would it? So one thing we know about it right off the top is that delta G, or the Gibbs energy, is going to be less than zero. And it's going to move towards zero as the battery drains, and the whole thing gets back to equilibrium, and then no energy flows at all. Okay, so the ones that we're going to be talking about, and probably you'll be building in the lab, use ionic solutions to conduct electricity, and also to provide kind of the means through which we're going to cause these reduction and oxidation reactions to occur. Okay, so when we get two electrodes in an ionic solution and we connect a circuit to them, we're connecting a source of electrons to an electron sink, or something that's going to oxidize under the conditions we've made it, and something that's going to be reduced. And the pulls between these two competing reactions, I guess reactions working in concert rather than competing, is going to allow the electrons to flow through the circuit. So this is the setup that we're going to call the galvanic or a voltaic cell. An electrolytic cell, on the other hand, would be doing the opposite. So this is an example where we would use electrical energy to drive things the other way. So we'd be pushing electricity into the system to get a reaction to occur that wouldn't ordinarily occur. So this would be where delta G is greater than zero. We have to do work on it to make it happen. Okay, but we're going to stick with the voltaic cell, at least for the first little while. And there's an image of it drawn in your notes, okay? So in the diagram as it's shown, I've got my pen up here. So we've got a zinc electrode and a copper electrode. Okay, so on the zinc side, we've got some zinc sulfate solutions. So there's going to be some zinc ions in solution as well as the zinc metal. Yeah. So the reaction here that we've already seen is we've got zinc going to zinc 2 plus and 2 electrons. Okay, so on the inset, it's showing the atoms coming off of the zinc electrode and just flowing into the solution as dissolved zinc ions. So this is where the oxidation reaction is happening. Oxidation. And wherever the electrode that hosts the oxidation reaction is called the anode. All right. And on the other side, so we watch the electrons. This 2 electrons are going to flow through the circuit, come over onto the copper side. Here we've got the copper electrode with some copper 2 plus in solution. And the reaction there, we're going to have copper 2 plus those 2 electrons that we got from the zinc turning into copper metal. Okay, so this is where we're going to pick up copper from the solution and start to add mass onto that electrode. Okay, so on this side we have the reduction, and this is always going to be the cathode. Not always the copper, but where the reduction happens is the cathode, okay? And how we're going to remember what happens where is we have an ox, okay? So let's draw an ox, okay? There's our ox. It's got some feet on it, okay. Not as good as one in class, maybe. Now it's got webbed feet. So there's an ox, and on the other side, we're going to remember the red cat. Okay, and if I can ever get my pen back. We're going to, no, that's blue. Red, please. There we go, okay. Red cat. This one's even fatter than the one we did in class, and it's grumpy about it. All right. Okay. So, oxidation happens on the anode, and red cat, okay? Reduction happens at the cathode. What else do we want to say about these guys? So the electrons are going to flow from the anode through the circuit. We can read there's voltage showing, so positive voltage flowing through the circuit into the copper. Okay, the electrons given off by the zinc, picked up by the copper. The zinc is oxidizing, it's dissolving into solutions, so that zinc electrode will get lighter over time if we were going to weigh it. The copper electrode is going to get heavier over time because it's pulling copper out of solution. The salt bridge right here in the middle, the point why we have it there, so there's some sodium and some sulfide there. It's just going to balance the charges. So if we're pulling zinc off of the electrode and it's going to be positively charged in solution, if we didn't have something to counterbalance that, the solution would just become more and more positively charged, and it would eventually stop the battery. Same thing on the copper side. By pulling those copper 2+ out of solution, the solution's it's eventually going to become more negatively charged, and the sodium is just traveling through that bridge over onto the copper side to make sure that the solution remains neutral. What else do we have to say about this? I think by now you will have set one up in the lab, so you'll see more or less how that goes. Moving on, so what are we doing here really? What we're doing is taking the Gibbs energy of the spontaneous reaction and we're using that for electrical work. We've already said the Gibbs energy is a measurement of work. So this is telling us how much work we can do with the reactions that we have between the two sides. So if we want to think about the potential difference, so the net difference in potential, we're going to use E for potential, measured in volts, is going to be the cell potential minus any kind of external load. So if there was something on the circuit that was going to cause electrons to flow the other way or slow them down, we'd have to subtract that from the total potential difference. But in this case, we're really just looking at this cell potential, okay? So bear in mind the E cell for a spontaneous reaction is always going to be positive. So we're going to see that as greater than 0. And bear in mind again that delta G has to be less than 0 for the same thing. So you can see that there's going to be a negative relationship between them eventually, which we will talk about. And the units are going to be in volts, okay? Which is the same as joules per coulomb. And so this is just 1 joule of energy per coulomb of charge. And you can, again, we're getting a little bit ahead of ourselves, but eventually we're going to use that to be able to transform or convert between the cell potential and the Gibbs energy that we get out of it. Okay, so standard cell potential, like we've seen with other things, we'll use this little degree sign up in the corner to make sure that we're mentioning the standard cell potential. This is going to be at a certain temperature. It's going to be where all concentrations are equal to 1 molar. What else are we going to do? Pressure, we'll just have it at 1 bar. Okay, and so for this zinc copper setup that we have, okay, so this will be to zinc 2+ and copper metal. The standard cell potential is 110 volts, or 1.10 volts. Okay, and that's what we're going to say for that. We'll start on the half cells and the standard reduction potentials in the next video. So thank you very much for watching, and I guess we'll see you next time.